I'm glad to present Professor Sören Schlichting today, who got his master's degree at Michigan State University. And I usually don't mention master's degrees in presentations, but in this case, it's exceptional because he was working with Scott Pratt at Michigan State University, and they did really a great work on charge conservation and RHIC and contribution to local parity violation observables that became quite famous. He got his PhD at Heidelberg University, although he started at Darmstadt University and then moved to Heidelberg University, finishing his PhD with Jürgen Bergers. After that, he was a postdoctoral research associate at Brookhaven National Laboratory from 2014 to 2016. He was also a Goldhaber Distinguished Fellow at BNL. He then had a research assistant professor position at University of Washington in Seattle until 2018. And since 2018, he is on a tenure track position at University of Bielefeld. From 2019, he is a principal investigator on the project related to non-equilibrium QCD nuclear collisions. And in the past, just a few years ago, actually, he served as a member of Chiral-magnetic effect in heavy-ion collision task force, which assessed the present status and recommendations for future strategies at BNL. With that, I'll give the microphone to Sören, so you may start.
Yeah, thank you very much, Igor. And so first of all, thank you very much for this kind invitation and really the great opportunity to present this here today. So today I'll be talking about non-equilibrium QCD processes in heavy ion collisions. And so basically what I'll try to do in this talk is, since this is a theoretical physics colloquium, I'll be a little bit more theoretical than usual, perhaps. So what I'll try to do is I'll try to summarize some of the progress that we have made in understanding somehow different patterns of thermalization of QCD plasmas. And then towards the end of the talk, come to how they affect our understanding of the very early stages of high energy heavy ion collisions. And so I should mention that there's also two very recent reviews on this subject, which I've listed for you over here on the title slide. Okay, so the outline of my talk is as follows. So since I didn't really know what kind of an audience to expect here in detail, I figured it would be best to start with a brief introduction and motivation. So why should we care about understanding thermalization processes in QCD plasmas? Then the main part of my talk will consist of somehow describing the microscopic and macroscopic features of thermalization of QCD plasmas with coupling. And towards the end of the talk, I'll then come to how they affect our understanding of the early time dynamics in heavy ion collisions with an emphasis on entropy production. And of course, I'll end with some conclusions and outcomes. Okay, but so let's first start with the motivation. And so for us, of course, the motivation comes from high energy heavy ion collision experiments. And there, of course, the overarching science goal is really that we want to explore the structure and dynamics of somehow the fundamental constituents of matter. So at the most fundamental level that we know about this today, this is described by the theory of strong interactions of quarks and gluons, which is quantum chromodynamics, QCD. However, of course, QCD has somehow the peculiar property that under normal conditions as we have it today, say, right, we don't really see the quarks and gluons as they are confined into color neutral bound states, such as protons, neutrons, pions, kaons, etc. So to actually get access to the QCD degrees of freedom, the fundamental degrees of freedom of QCD at least, what we need is actually very extreme conditions. And so this can be achieved in somehow a number of different ways. Either we can look at somehow these hadronic bound states, such as the proton, with a very, very high resolution to try and disentangle its partonic content, which is the strategy that's taken, for instance, in deep inelastic scattering experiments. Another possibility is to actually take nuclear matter as it is and heat or compress it to very high temperatures. And so this is illustrated over here on the right, where I show a sketch of the QCD phase diagram. So different phases of QCD strong interaction matter as a function of the temperature and the baryon chemical potential on the horizontal axis. And so it is firmly established from first principle lattice QCD calculations that at temperatures on the order of around 155 MeV, the ordinary hadron gas, or the hadronic degrees of freedom, they undergo a smooth crossover transition into a phase that we call the Quark-Gluon plasmas, where really quark and gluon degrees of freedoms are somehow liberated from their hadronic bounds, from the hadronic bound states. So how can we create such extreme conditions with such extremely high temperatures? Well, there's a number of possibilities. So on the one hand, of course, our early universe, as it was cooling down, was following somewhere a trajectory here at presumably low net baryon chemical potential down the temperature axis. And so, but of course, that doesn't give us really any immediate prospects for observation, since we have to live with the universe that it is today. So the way to actually recreate these conditions today on Earth is to explore these extreme states of matters in high energy heavy ion collisions. And there's current experiments at the high energy frontier being performed at the Relativistic Heavy-Ion Collider at Brookhaven, at the LHC at CERN. And there's also, of course, lower energy experiments at GSI FAIR and future facilities such as NICA. So what is done in these experiments is that atomic nuclei, such as gold or lead, they are accelerated to very high energies, up to TeV energy scale. And then they are basically collided head-on in order to create somehow regions with sufficiently high energy densities, which then eventually correspond to these temperatures. And this is kind of characterized, shown here by these blobs in terms of the phase diagram. Now, of course, life is not as easy as it seems here, because if you look at the actual outcome of a heavy ion experiment, then this will somehow look something like what is shown here over on the bottom right, which is an event display from the CMS experiment, lead collision at CERN, where you see here really thousands of tracks of particles produced and energy deposition in the calorimeters. And so without going into much detail of these pictures, the only reason that I'm showing is that to really visualize you that somehow when we actually deal with heavy ion collisions, this is not simply a transit trajectory in the phase diagram, but to really learn something about QCD matter from heavy ion collisions requires in general a very profound understanding of the space-time dynamics of the collision. Okay, so let's talk next about the dynamics of heavy ion collisions. So where do we stand with this today? And of course, what we'd really like to do is we'd like to take the QCD action and calculate the outcome of a heavy ion collision. Now, it turns out that this is far from being possible. In fact, the dynamical description of heavy ion collisions from the underlying theory of QCD really remains an outstanding challenge. And so when we actually try to describe these experiments, then there's somehow a standard model of nucleus-nucleus collisions, which is based on a macroscopic description of the space-time dynamics. And so that to a large extent relies on the fact that the complex reaction dynamics that goes on in these experiments is subject to a very clearly defined somehow separation of time scales at different things happening at different times. And so this is what I'm trying to illustrate here in this central panel. So before the collision, of course, you have these somehow highly Lorentz contracted nuclei. And so as they approach each other, they will eventually collide and mostly pass through each other. But the time scale it actually takes for the two nuclei to collide at high energies is very, very short. So it's typically much less than a fraction of a Fermi. And so you can basically think of this as kind of an almost instantaneous process. Now, in the collision, of course, these nuclei deposit somehow a highly excited state of nuclear matter, which initially is far from equilibrium. And so the common understanding, and that is in line with phenomenological extraction, is that it takes on the timescale of about a Fermi over C for this non-equilibrium matter to evolve to a state which is then sufficiently close to equilibrium such that it can be described by hydrodynamics subsequently. So after about a Fermi over C or so, the matter created in a heavy ion collision, so somehow deposited in the center of the collision region, then continues to go a hydrodynamic expansion whereby essentially the plasma that you have created expands first along the beam direction, later on into the transverse direction. And by this expansion, this matter, of course, expansion into empty space, the matter cools down until on a time scale of about 10 Fermi over C, you reach temperatures which are no longer high enough for the Quark-Gluon Plasma to exist. And so your partonic degrees of freedom somehow recombine into hadrons, which then undergo a few rescatterings before eventually they will free steam into the detector. And so by looking at this, by looking at kind of this sketch over here and somehow comparing the different time scales, right, and you will see for somehow most of the lifetime of the system, right, the space-time dynamics of a heavy ion collision is actually dominated by this hydrodynamic expansion of the Quark-Gluon plasma. And so in general, there's a very extremely successful phenomenology based on hydrodynamic models of heavy ion collision. So in the past, what has typically been done is that essentially one has taken somehow a parametrized initial state of the collision somewhere around here, 1 Fermi over C, and then simulated the hydrodynamic expansion of the QGP, subsequent rescattering, and tried to describe heavy ion observables. And indeed, this is a very successful concept, and one can learn a lot of things about the equilibrium and transport properties of the Quark-Gluon plasma. Now, if you ask yourself about what kind of an effect can somehow this early stage have here, then generally the problem is that since this stage doesn't last very long, it will have a small effect on somehow the typical observables that we consider in heavy ion collisions. Nevertheless, you would like to somehow include this into your theoretical description, because from a theory point of view, really what you would like to do is you would like to simulate the entire, or be able to describe the entire reaction dynamics really from the very beginning to the very end. And so from a theoretical point of view, the description of this pre-equilibrium dynamics is really highly desired. Okay, so with this being said, I think there are really very good, at least 2 very good motivations for trying to understand equilibration processes of QCD plasma. And so the first one, as I just introduced, comes from high energy heavy ion collision, where somehow the big or central question is, how does it actually come that somehow following this initial violent reaction of 2 nuclei colliding, very shortly after we can employ a macroscopic description of the system as a viscous fluid. And so how does that emerge from the non-equilibrium dynamics of somehow this primordial far from equilibrium plasma, which was created very early on in the collision, essentially directly after the collision. While clearly in heavy ion collisions we deal with QCD plasmas, there's however also another context where we should in principle be thinking about equilibration processes in QCD plasmas, or even well, maybe perhaps equilibration in the entire standard model, and that is in the early universe. So I showed you in the beginning that the trajectory of the early universe also encompassed a very hot stage. And so essentially the question in that context that one would like to understand would be, how is the standard model matter produced and also equilibrated somewhere between the end of inflation and Big Bang, so at the end of inflation, where the whole energy of the universe was contained in the inflaton, and Big Bang nucleosynthesis, where you really need the equilibrated standard model matter as we know it. And so, although I won't have to say too much about this, about the properties in the early universe today, it is clear that somehow, you know, the progress we make in understanding thermalization patterns of QCD plasmas and heavy ion collisions could eventually be applied also to somehow studying processes in the early universe. Okay, so with that being said, that concludes somehow my motivation of the task. So let's then dive right in and somehow try to understand patterns of thermalization of QCD plasmas. And so, so first of all, I have to say, well, what are some of the theoretical tools that we have available that or at our disposition to study these kind of phenomena? And so the first thing one should say there is that somehow in contrast to describing QCD matter that is static, so that is not moving, or so static properties of QCD matter, where we can employ lattice QCD and really get first principle answers, there's no analogous approach to studying non-equilibrium processes, actually in any interacting field theory, let alone a theory as complicated as QCD. Nevertheless, with regards to high energy QCD, which is what we're interested in here, there are still two limits where you can actually perform first principle studies, and these are feasible. And so these are, on the one hand, the weak coupling limit of QCD, where, as you would expect, you employ a description in terms of the fundamental degrees of freedom of the theory, so quarks and gluons, and you can describe non-equilibrium dynamics based on kinetic theory, or in some cases also real-time lattice simulations in the classical limit. The other frontier where a lot of progress has been made in understanding non-equilibrium properties of gauge theories is the strong coupling limit at large Toft coupling of theories which are not QCD but related to QCD, where you can have a holographic description for strongly coupled plasmas, for instance, in n equals 4 superionis. Now, one should clearly say here that, well, neither the weak coupling limit of QCD or the strong coupling limit in supersymmetric theory exactly corresponds to the situation that we would wish to describe in a heavy-ion collision at RHIC, at say RHIC or LHC, right? So irrespective of what approach we choose, we eventually will have to extrapolate to the point that is relevant to present-day collider experiments. So the direction that I'll pursue in this talk is that I'll use a weak coupling description based on leading order QCD kinetic theory, which in the weak coupling limit becomes in principle exact, to describe the non-equilibrium dynamics of the Quark-Gluon Plasma. And we'll then, of course, at the end of the day, as I said, we'll have to extrapolate these findings to realistic coupling strengths when actually addressing heavy-ion collisions. But it turns out that even if you actually study this problem at weak coupling, this is actually a rather interesting problem by itself, and so I'll be saying quite a few words about that. Okay, so what does the theoretical description of non-equilibrium QCD then look like? And so in the weak coupling limit, you can apply an effective kinetic theory of QCD, and we'll work here to leading order, where the dynamics of the system is then simply described in terms of phase space density of quasi-particles F, so phase space densities of quarks and gluons, which evolves according to a standard Boltzmann equation, where you have somehow the ballistic motion of particles and collisional processes that change the current state of the system. And so, while of course, kinetic theory is a commonly used tool in describing non-equilibrium systems, say also in condensed matter systems, there are several characteristic features of QCD which actually make the processes that occur quite unique to, well, at least non-abelian gauge theories. And so that is on the one hand that, of course, we're dealing with regards to QCD, we're mainly dealing with ultra-relativistic massless particles. And so in the studies that I'll be showing, we'll consider gluons as well as the three-light quark flavors. And the other thing that makes this very particular to QCD, or non-abelian gauge theories, I should say, is the fact, is the structure of the interactions that one has in QCD. So it turns out that due to the structure as a non-abelian gauge theory, in QCD, both elastic and inelastic, so elastic are particle number conserving 2-to-2 scatterings, and inelastic, which are radiative processes, they contribute at the same order. And so when describing somehow the dynamics of the system, you have to take into account essentially all 2-to-2 scattering processes between quarks and gluons, as well as all possible radiative processes. Now, where does this come from? Well, if you look at the elastic scattering processes and you just calculate the perturbative matrix elements, what you'll see is that elastic scatterings, where somehow there's a very small momentum transfer, they actually have a divergent rate, which of course in the medium is regulated by Debye screening. But then even though these processes are screened, they still happen very frequently in the plasma, and each small kick that the particle gets can induce additional radiation. And for that reason, these inelastic processes also appear at the same order. And in fact, these kind of elastic scatterings with small momentum transfer, they can occur so frequently that actually when calculating the induced radiation, you in fact have to account for somehow a coherence effect between multiple scatterings, the so-called LPM effect, which one can include via vertex resumations. And so it is kind of this structure of this complicated structure with medium-dependent matrix elements, which really makes this a rather non-trivial problem. And so, as you can see, even though somehow the kinetic theory of QCD at leading order was written down almost 20 years ago from today, it's really only been in the past 5 years or so that numerical solutions to these kinetic equations have really become available, and so that's where a lot of progress in understanding thermalization has derived from. And so whenever I'll present results here, I'll present essentially numerical solutions to this integral differential equation with self-consistently determined in-video matrix elements.
Sören?
Yep.
Quick question.
Yes.
Device screening is essentially like resummation of hard thermal loops for the gluons. What about the thermal masses for the quark?
Yeah, the thermal masses of the quark are also of course included, where you have essentially when you have a T or U channel quark exchange. Yeah, of course you have to include this as well. Yeah.
Okay.
Yeah, and so so if you really want to know about the details, we do this we do this assuming essentially isotropic screening, because there are problems in principle if you consider anisotropic plasmas. Okay. Okay, that's a real subtlety. Okay. Okay. Good. So this is the basic framework, and so let's go out and try. So based on this framework, now try to understand somehow. What can be patterns of thermalization processes in QCD plasmas. And so before addressing the full complexity of the thermalization in a heavy ion collision, it is actually interesting to start with somewhat simpler systems. And so for the next few minutes or so, I would basically like to discuss what has emerged as an understanding of the thermalization in homogeneous and isotropic QCD plasma. Okay? And so there's been actually some nice work about 10 years ago, which kind of classified different systems. And so it turns out if you consider systems which are somehow not close to equilibrium, such they would kind of directly relax back towards equilibrium, there are essentially two qualitatively different cases of non-equilibrium systems that you consider, which I'll refer to as an overoccupied plasma or an underoccupied plasma. So what characterizes an overoccupied plasma? So for an overoccupied plasma, if you look at the phase space distribution of gluons, say, as a function of the momentum, then overoccupied plasmas, they are characterized by a large number of sort of low momentum gluons, such that the typical momentum of each particle is much smaller than the corresponding equilibrium temperature of the system. So if you compare the initial state in green to the corresponding thermal state of the system, then you'll see, okay, you have all the energy is initially stored in somehow low momentum degrees of freedom. And this is kind of a typical situation that may arise for instance, when your system is subject to instability that typically generates somehow such a large phase space distribution at a characteristic momentum scale that I'll call Q. Now, the opposite is the case in an underoccupied plasma. So here you're dealing with a situation where instead of having a large number of low energy degrees of freedom, you have very, very few high energy degrees of freedom. So one way to think about this is, say, you have a collection of very highly energetic jets, right? But they're very few, okay? And so, so in contrast to the corresponding equilibrium state, the energy is stored by very, very few high energy degrees of freedom. Okay, so let's have a look at somehow how these systems thermalize. And so let's first start with the overoccupied QCD plasma. So in the overoccupied plasma, you initially have very many particles present in the system. And so for that reason, these particles can actually interact very strongly with each other. And so the initial scattering rates are strongly enhanced compared to a typical equilibrium scattering. And so what will happen is that actually very, very early on, the system will essentially have an effective memory loss where it completely forgets about its initial conditions since the scattering rates are very large. And so it will forget about the details of the initial state even before the system thermalizes. Now, while such a memory loss sets in very early, what is significantly harder is to actually take these low energy degrees of freedoms, right? But increase the momentum of each particle such that their momentum becomes on the order of the temperature. And so if you look at somehow the evolution of the phase-space distribution of the gluons as a function of temperature, starting say from an initial state over here, then you'll see initially all the energy is sitting in the low momentum regions. But then as the system evolves, what happens very quickly is that the system essentially establishes more or less thermal infrared spectrum, but then the maximum energy that each particle can carry is still rather small. Now, as the system evolves, essentially what happens is that the energy of these low momentum particles is kind of transferred to higher and higher scales. So particles gain momentum or energy by successive scatterings. But what is interesting about this is that the fashion in this happens actually repeats itself over and over again. So if you actually compare somehow, say, the slight green distribution to the distributions that you have at later times, what you'll find is that they can actually be scaled on top of each other. And so what has really happened is that there's a somehow self-similar evolution of gluons, which is associated with this energy transfer from the low momentum sector, so the infrared, towards the ultraviolet. And so that is very similar to processes that you see, for instance, in decaying turbulence. And so you can characterize this entirely. So the spectrum at these intermediate times can be characterized entirely in terms of a very simple scaling form, where essentially the typical momentum of each particle increases as a function of time as you evolve, while the shape of the spectrum stays intact until eventually this energy transfer to the ultraviolet is completed. And that is when the system really thermalizes and you approach somehow the unique Bose-Einstein equilibrium distribution. Now, what about quarks in this system? And this is really the novelty of this study that's currently in preparation with my postdoc, Judging Du, is in the case of an overoccupied system, of course, you have a large abundance of gluons with occupation numbers typically much larger than 1. In contrast, of course, the occupation number of quarks is always limited to unity due to the Pauli exclusion principle. And so for that reason, you will typically have very, very few quarks present in the system. So initially we took no quarks present in the system, then of course a quark population builds up. But the quarks in this case really play a subdominant role and essentially simply follow the behavior of the gluon distribution such that at each instance of time, you kind of produce as much quarks as is needed. Okay, so as I already alluded to this, there
is a question here.
Yeah.
There's a question here. So from Thomas Schaefer, he asked, what happens for more reasonable values of decoupling?
Shall we go here? That's on this slide, actually.
Okay.
So Thomas, I hope I'll answer your question. Please, please come back after the slides if I didn't. So the subsimilar scaling behavior is, as I said, it's associated with the energy transport towards the ultraviolet, and this is really, to a large extent, analogous to direct energy cascades that we see in decaying turbulence. So to a certain extent, you can picture this like turbulence in the fluid, where say you steer your pot of fluid, you will induce somehow these large eddies, right, which will then back up into smaller and smaller eddies, right? And so it's exactly the same thing that is kind of happening here, except that it's of course the dynamics of QCD that's underlying this and not that of capillary surface waves. Now, the results I showed over here, as Thomas pointed out, they were performed, of course, in the strict recoupling limit. But of course, we would also like to understand what's happening at more reasonable values of the coupling. And so, rather than showing you some of the pictures of the phase-space distribution, it's actually easier to compare the behavior of different coupling strengths by comparing somehow the evolution of the characteristic scales. So if we focus here on the red curves, so different panels here show results for different coupling constant. The red curve shows the average energy per particle. And so what happens is initially particles have very low energy. The system then quickly forgets about this initial condition. The average energy per particle increases according to a power law with an exponent that you can also calculate analytically until eventually the energy per particle reaches its equilibrium value, and that's when essentially the system thermalizes. Also shown here is the scattering rate, which is T star, so this is the black curve. And so you can see initially the scattering rate is very large, but then eventually increases towards its equilibrium value. Okay, so now if you actually compare this and you crank up the coupling strengths, of course, at some large values of the coupling, it's not clear that leading order description really is particularly accurate, but at least if you do it within the leading order description, okay, what you'll see is that exactly the same pattern actually stays intact. So even at a coupling strength of 10, with the same separation of scales as before, you still find, okay, that there's actually quite a window where this kind of a scaling sets in. And so, in fact, the same scaling phase behavior persists even for moderate large values of the coupling constant.
Another question, what is the physical scale on the x-axis coming from Thomas?
Yeah, thanks. Yeah, so thanks for pointing this out. So what's shown here is the evolution time, and that's shown in units of lambda squared. So lambda squared is the coupling constant, g squared. So lambda is g squared nc. So that's the coupling strength, and then to make it dimensionless, it's the equilibrium temperature. Okay.
But doesn't have any physical sort of connection to.
Yeah, so you can you can think of it as time in units of the large angle scattering rate of the equilibrium system.
Right. Okay.
Yeah, so that's exactly why we chose this lambda squared t. Yeah, and so that's also why you can see that, you know, even though the coupling strength here is very different, right? The overall time scales when you approach equilibrium are actually very comparable between the different systems. Yeah, so eventually the system equilibrates on the time scale of one equilibrium relaxation time, essentially. So one equilibrium scattering rate. Okay, and so that's actually that's actually kind of what was supposed to be told on this slide. So for the first case of generic far from equilibrium initial state, namely that of that overoccupied plasma, the basic thermalization pattern looks like this. You have an initial state where the energy is carried by low momentum particles. Since they interact quickly, they forget about their initial conditions. There's a self-similar cascade, self-similar direct energy cascade set off, whereby energy is transported somehow from this low scale to the high scale. This is mediated by elastic scatterings as well as these kind of 2-to-1 mergings. And the cascade basically continues until eventually the average energy per particle is on the order of the temperature, and that's where the system thermalizes. So the thermalization time in this case, as the scattering rates goes down, is actually given by the ultimate approach towards equilibrium, and so it's just given by somehow the equilibrium relaxation rate, which is the time scale for large angle scattering in QCD. Now, let me say that this kind of a pattern that is shown over here is actually something that is not very particular to QCD, but in fact, it turns out that the same kind of pattern actually emerges in a variety of far from equilibrium systems. And so there's a multitude of systems that's been studied where essentially you start with a state of high bosonic occupancy, so far from equilibrium state, and then follow the evolution. And so they all kind of follow a very similar pattern. In particular, this has been established for relativistic and non-relativistic Bose gases for scalar interactions. And so this is really nothing that is particular to QCD, okay? But it's kind of a feature that emerges in many different kinds of non-equilibrium systems. Okay. So far for the overoccupied QCD plasma. Now, what is more particular to QCD is actually if you study the equilibration of an underoccupied QCD plasma, so a system where initially you have very few very highly energetic particles. And so the basic pattern is illustrated over here. So the plots are the same. Again, I show you on the left the gluon distribution, on the right the quark distribution, okay, as a function of the momentum at different times of the evolution. So in this case, we started with somehow a collection of high energy quarks shown here by this red distribution, okay? And so the way that this system will thermalize has a very particular pattern, which we call bottom-up thermalization, and that was actually first worked out quite a long time ago by Rolf Bayer and collaborators. So basically, what will happen is that these somehow highly energetic particles, they can interact with each other, okay? And while somehow elastic processes don't really affect them very much. The fact that they're interacting with each other triggers the emission of radiation. Okay, and so what will happen very quickly is that these hard particles, they can emit soft quarks or gluon, thereby establishing here somehow a characteristic radiation spectrum of QCD in both the quark and the gluon sector. Now, of course, these low energy gluons that you create, right? They are much more affected by interactions with the residual, with the remaining hard jets, okay? And so therefore they can actually thermalize relatively quickly, meaning that sort of at intermediate stages of the evolution, you already kind of form a soft thermal component of your spectrum, but then the high energy tails are not yet populated. Now, once you have established this kind of thermal bath at low momentum, essentially the situation is very similar then to that of a highly energetic jet traversing a thermal medium, okay? And so what will happen is that basically these remaining hard guys, these remaining hard quarks, they will lose energy to the thermal bath, and so essentially energy is transferred then from the hard quarks to the soft thermal medium. I think essentially at the end their distribution is eaten up, and again the system thermalizes.
Sören, I have a question. Yep. The quick question is about this. Very low energy bosonic distributions, they are very sensitive to the final equilibration temperature. How do these bosons know that that will be the final temperature if you have such an overoccupied?
Oh, no, at intermediate times, so at intermediate times the temperature is actually not the same. So the temperature, so as the hard particles continue to lose energy to the bath, of course the bath heats up. And actually,
but your time dependence doesn't seem to change much the low energy distribution of the.
Yeah, this is because here in this case the separation of scales is not very large, right? So the initial energy is I think 3 times the temperature here. If you go to larger scale separations, you see this more clearly. Unfortunately I don't have the plot, but it will be in this paper. Okay.
Okay.
Yeah. Okay. So in this case, so what we see that in contrast to the overoccupied piston, first important point is that actually radiative processes play a very important role. They are actually what somehow really drive the energy transfer from the ultraviolet to the infrared. That is really why this kind of thermalization pattern is very unique to non-abelian gauge theories such as QCD. Now, there's a few more things that you can actually learn about this process. So for the overoccupied system, I mentioned the relation to turbulence. And the same actually, there's actually an interesting relation to turbulence also holding here for the underoccupied plasma. Namely, it turns out, if you study in more detail this process of how does the hard quark lose its energy to the soft thermal bath, then it turns out that this actually does so by, again, a scale invariant energy flux, somehow from the hard scale of the quark all the way to the soft scale of the temperature of this bath. And so really what that means is that rather than somehow directly radiating soft gluons to transfer the energy from the jet to the medium, the system actually undergoes multiple successive splittings, okay, before eventually you kind of get soft particles on the order of the medium scale. And so it turns out that if you actually make the separation of scales large enough between somehow what is the energy scale of your initial particles and what is the temperature scale of the medium, then indeed you recover a lot of the standard features of turbulence. For instance, what you'll see is that actually the spectra at intermediate times, they are described by the Kolmogorov-Zakharov spectra of weak wave turbulence. And what is also interesting is that somehow particles with intermediate energy, since they have kind of undergone multiple successive branchings, they really forget about the initial structure of the hard distribution. So for instance, this actually becomes insensitive to whether initially you started off with a quark or a gluon. And so for instance, also if you ask about what is the quark to gluon ratio somewhere at intermediate scales in the cascade, then you'll actually find that this is somehow determined by a balance of radiating gluons versus creating quarks. And so this is kind of shown over here, where actually we did this for an actual jet. You can calculate what this should be based on the balance of gluon radiation and splitting into a quark, and you find that indeed for somehow for evolutions which are where somehow the jet is not fully eaten up but sufficiently quenched, there's a range of momenta where actually this approximate balance holds. Okay, so wrapping this up, so how does an underoccupied QCD plasma thermalize? So in this case, we have an initial state which is also far from equilibrium, but this time features very, very few high momentum excitations. These high momentum excitations will first emit soft radiation, which leads to a creation of a soft thermal bath. And subsequently, the thermalization works just as jet quenching, okay, where essentially the remaining hard particles continue to lose energy towards the thermal bath via somehow this inverse energy cascade of multiple branchings until eventually these guys have lost all of their energy and the system is in thermal equilibrium. Now, what is interesting about this is that for the overoccupied plasma, I told you that the thermalization time of the system, okay, is essentially determined by the equilibrium thermalization rate, okay. It turns out that for these underoccupied case systems, this is not the case, okay. Namely, the thermalization time is actually larger than this equilibrium scattering rate, the inverse of the equilibrium scattering rate, by a factor which depends on the initial energy of your high energy particles. And so this has a simple reason. This is simply because the emission of radiation from these high energy particles is slower as compared to the typical processes that happen at the temperature scale. And so for that reason, this bottom-up thermalization is delayed due to the reduced splitting rates of these high momentum particles. Okay, so this concludes the rather theoretical part. Are there questions here?
I think you just...
Question.
Yeah, go ahead.
Is color sort of traced over, or
yeah, spin and color average?
So
yes.
there is no color thermalization or anything like that, right?
This calculation, I mean, kinetic theory is a spin and color averaged theory.
Okay.
Okay. I also see that I'm spending a lot of time here, so I should probably speed up a little bit. Okay, so now that we've understood somehow basic patterns of thermalization of these plasmas, we can I hear some.
I assume there is another question. But there is another question which was in the chat coming from George Fernandez Soriano. Which situation, under versus over occupied, is more realistic in heavy ion collisions?
Okay, this comes on the next slide. Now we move on to heavy ion collisions, okay?
Okay, let's go there.
Okay, good. All right. Okay, so now that we understand the basic patterns of thermalization in QCD plasmas, we can move on to try and understand the dynamics during the early stages of heavy ion collisions, okay? And so you may first ask what is different about what you just described. And so the key difference is that somehow the non-equilibrium plasma that's created immediately after heavy ion collisions is subject to a rapid longitudinal expansion, okay, where essentially some of the plasma created expands outwards as the nuclei separate from each other. Okay. So what we'll do to try and understand this process, we'll look sort of at a little cell here in the middle, okay? And so basically what will happen here is that the particles which somehow have a high velocity or high momentum in the longitudinal directions, they'll quickly escape this region in the middle, okay? And so what that means is that the plasma that's created in the middle will actually be highly anisotropic with the typical transverse momenta much larger than the longitudinal momenta. And also due to the fact that the system is expanding, it becomes increasingly dilute as we speak. Okay, so let me skip all the other technicalities. So now, how does the thermalization of this kind of system proceed? Okay, and so so shown over here are now sketches of the phase-space distribution of the evolution of gluons in this case in an expanding QCD plasma. Okay. And so, well, since this is a 3D distribution now, what's shown are somehow these colorful plots of longitudinal momentum on the x-axis and transverse momentum on the y-axis. And so it turns out that even if the system initially is overoccupied, okay, it will actually not have sufficient time to thermalize, okay, but it will actually become underoccupied before it is able to approach equilibrium. And so actually what happens in this case is very, very similar to the underoccupied case. Namely, you have this kind of relatively hard mini jets, okay, which emit softer and softer gluons, okay, such that eventually you create an anisotropic but sufficiently energetic soft bath, okay. So at intermediate times, what you see is essentially you see some remnants here of the hard gluons and their radiation spectrum, but you create this soft bath, and essentially these remaining hard particles, they continue to lose energy towards this soft bath, which itself starts to isotropize via elastic scatterings, okay? And eventually you create an ensemble of somehow lower energetic particles with a more isotropic distribution. And so this is now really numerical calculations of a scenario that has been predicted long ago by Bayer et al.
Sören?
Yep.
Here is the question from Christoph Kudak.
Yep.
Are 2-to-1 processes relevant for thermalization of underoccupied plasma?
So the answer is yes, they are in the low momentum region, right? So once you're at the scale where the system thermalizes, this is always, you have to include the inverse processes. Yeah. Okay. Yeah. If you just want to describe the hard structure, then this is essentially irrelevant. Yeah, but at the low scales, they always are. Yeah. Okay. So this is somehow the microscopic picture of the evolution of these expanding systems. Now, what we set out to answer in the beginning is the question of how can we understand the onset of hydrodynamic behavior in a heavy ion collision. So to answer this question, it's first good to actually think about what hydrodynamics actually does. Okay, or what is hydrodynamics? So hydrodynamics describes the macroscopic evolution of the energy momentum tensor in the simplest cases, or possibly other conservations, and it is based on the conservation laws. These are things that are always valid, and so-called constitutive equations, which are typically obtained in an expansion around local thermal equilibrium. Okay, and for this there are essentially two types of expansion parameters: the Knudsen number, which is a ratio of somehow microscopic to macroscopic timescales, so say of the relaxation rate to the expansion rate of the system, and the inverse Reynolds number, which is a ratio of dissipative, so non-equilibrium corrections to the energy momentum tensor, to equilibrium to the equilibrium energy momentum tensor. And so really the main question in this setup, where I'm currently neglecting the transverse expansion of the system, is to understand how this somehow highly anisotropic systems at early times eventually evolves towards a more isotropic state, that can then potentially, so where then the non-equilibrium corrections to the energy momentum tensor are smaller, and the system could potentially be described by hydrodynamics. Okay, so of course, based on these microscopic calculations, you can then calculate the evolution of the energy momentum tensor. And so that is shown over here in the left panel, where the evolution of the longitudinal pressure, energy density, and transverse pressure are shown as a function of time in such an expanding system. Okay, so let's look at the longitudinal pressure. So basically what you find is initially systems highly anisotropic, okay? Then the longitudinal pressure picks up, but it really takes a very, very long time before the system really reaches a truly isotropic state, and the longitudinal pressure comes comparable to the transverse pressure. Now, nevertheless, if you compare this to the theory of hydrodynamics, okay, what you find is that actually hydrodynamics is able to describe even these very anisotropic systems. So the colorful lines here show results from kinetic theory calculations. The black line is the prediction from second order hydrodynamics in this case. And so what you find is that actually by a time which here in these units is 1.5 or so, or 1, essentially, despite the fact that the system is still highly anisotropic, it becomes amenable to a description in hydrodynamics. Now, as I said, there are different calculations shown over here, okay? And so these different colorful lines, they correspond to kinetic theory calculations at different coupling strengths, somewhere in the range between 5 and 20, which are sort of moderate coupling strengths. And so what is very interesting to observe is that if you actually compare these calculations not simply as a function of time, but in units of the equilibrium relaxation rate, which is determined over here as by the shear viscosity and the temperature of the system, then what you'll find is that simulations at these very different coupling strengths, they actually all lead to kind of the same evolution towards hydrodynamics, and by construction they have the same hydrodynamic asymptotics. And so actually the sensitivity that you find to the details of the coupling constants are relatively small when you phrase things in terms of physical units. And so that is what really gives us confidence then also in extrapolating our findings to realistic couplings. Now, what we see is that hydrodynamics becomes applicable on the order of approximately 1 equilibrium relaxation time. That's when hydrodynamics starts to describe the kinetic theory calculations. And so if you convert this then into somehow physical units, where you basically have to say what is the shear viscosity of the system and how large are the temperatures here, then you find that, okay, this time scale is roughly on the order of 1 Fermi or so, which is in line with earlier phenomenological estimates. However, what is the real, what is the real upshot here is that by the time that somehow hydrodynamics becomes applicable, you can see that, for instance, the longitudinal pressure and the transverse pressure, they are still very, very different, right? So they still differ by kind of order 1 type of contributions. So actually what you thought to be your expansion parameter, such as the Reynolds number, is still of order 1. Likewise, the Knudsen number, which in this case you can simply think of what is plotted on the x-axis, is also of order 1. And so really, really what this indicates is that actually the range of applicability of viscous hydrodynamics simply seems to be somewhat larger than you may naively anticipate from simply looking at its expansion parameters. And so this kind of surprising effectiveness of viscous fluid dynamics, this is by no means new to somehow these weak coupling calculations that I've shown here. In fact, it was first found in holographic calculations at strong coupling. And so this is really what has somehow emerged as our global understanding, that nowadays we don't believe that we create a system which is somehow terribly close to thermal equilibrium in heavy ion collisions. But we can describe it by viscous hydrodynamics, because viscous hydrodynamics properly captures the residual non-equilibrium effects. Okay. How much time do I have left?
Well, you could go for another 10 minutes or so.
Okay, good. That would be great, actually. Okay. So we can now try to take this understanding and actually put it into work to now not only describe the hydrodynamic expansion of the QGP, but really do a proper calculations of including the pre-equilibrium stage. And so over on the right here, this actually shows you an example of such a calculation where really an initial state calculation describing particle production was matched to a kinetic theory calculation that was then matched to hydrodynamics, and thereby you can really describe the entire reaction dynamics from beginning to end. Now, it is nice that you can do this, okay, but the upshot of this whole thing is that typically when you include the effects of this pre-equilibrium dynamics, they are, as you may have expected from the fact that the stage doesn't last very long, they are generally very small. And so this is, you can see this as both good news and bad news, right? Because on the one hand, of course, this is great news for if you want to learn about equilibrium and transport properties of the QGP during the hydro phase, because you can do so without encountering large uncertainties from the early time dynamics. But of course, it's also sort of a pity, because it also means that it's difficult to gain access to the early time non-equilibrium dynamics by studying heavy ion collisions. Okay, there's one, and that's going to be my last topic. There's one exception to this though, okay? And that relates to entropy production in heavy ion collision. And it's intuitively clear why this should be the case, because I mean, as we all know, entropy production occurs only when the system is significantly out of equilibrium, okay? And then in heavy ion collision, this is primarily the case at very, very early times. So the thing is, okay, now you may ask, okay, entropy reduction is fine. Is this something I can measure? And it turns out that entropy reduction is not only dominated by early times, it is also something that is actually more or less directly accessible by a very simple measurement, namely simply the measurement of how many charged particles are produced in the collision. Okay, and so schematically, what happens is that what happens during the non-equilibrium stage is that the initial energy that is deposited in the collision thermalizes. It is converted into the entropy of the thermal fluid, okay, which then, since the fluid expands at a very low entropy, this is a nearly isentropic expansion, okay? And then finally, when the QGP turns into a hadron gas, that entropy is converted into charged particles by simply counting the entropy per charged particles in a hadron gas. And so one of the nice things is that since we now understand what is happening during this, this early non-equilibrium stage, we can actually kind of make these relations explicit and really connect the initial state that was there at the very beginning of the collision with the measurement of charged particles at the very end of the collision. So I'm going to keep a couple of slides here. Feel free to ask what you come to, or how I get to this relation. Okay. But so you can basically work this out. So we know the evolution of the energy density throughout the system. We can map this to the entropy at the hydrodynamic stage and then convert that into charged particles. And so what you end up is sort of a relation like this, which then really relates the charged particle multiplicity with the initial energy per unit rapidity of the system. Now, what is interesting about this is that so this relation includes a bunch of prefactors. So let me say on somehow what does the conversion of the initial energy into charged particle depend on? And so first of all, it depends on some equilibrium properties of QCD, such as the number of charged particles per entropy in the hadron gas, that's around 7. The equation of state of the system at the time when the system thermalizes, so that's given by the effective number of degrees of freedom, that's around 40. Okay, but it also sensitively depends on a few non-equilibrium of transport properties. So there's some kind of, so since this depends on the pressure evolution at early times, you can actually characterize this by a constant here, which is, this is a genuine non-equilibrium effect, which is surprisingly well constrained. But it also depends very, very sensitively actually on the shear viscosity. So you can see that this is directly proportional to the shear viscosity to the power of 1/3. And so it's not like 1 plus shear viscosity, no, it's directly proportional to that. And that is related to the fact that somehow the shear viscosity determines how quickly thermalization happens, and that in turn determines how efficiently you can convert your initial energy into entropy. So it depends very sensitively to the shear viscosity, okay? And if you actually want to make this relation, then unfortunately, this is perhaps a parameter that is not actually that well constrained in the relevant temperature range, which would be temperatures, which would be sort of the very initial temperatures. So say somewhere around 40 C or so for LHC experiments. Now, of course, it also depends directly on the initial state energy density, actually to the power 2/3. And so, of course, if you know if all parameters except one very precisely, right, then you can determine the others. But it turns out that both the shear viscosity and the initial energy density are things that we don't know that well. So if you were to think about somehow calculating actually what is really the initial state energy density, what you will say, based on a perturbative QCD approach, then you would encounter significant uncertainties from small x TMDs, but also a potential for somehow large perturbative corrections. Nevertheless, I think this is extremely important, and to somehow show you having this kind of relation really shows you the impact of the pre-equilibrium stage, and to somehow illustrate this a little bit more, I've kind of inverted this formula, okay, and instead extracted the initial energy density from the measured charged particle multiplicity, okay? And so on the left, I show this for gold-gold collision and RHIC, right? This lead-lead collisions at the LHC, okay? And of course, if you look at the energy per unit rapidity, this is also something that is measured in a big experiment. And so you can compare the initial state energy per rapidity to the measured final state energy per unit rapidity. And so the gray bands here correspond to extractions of this initial state energy. where we varied the shear viscosity and these non-equilibrium parameters within the anticipated uncertainty margins. And so you can see essentially two things. On the one hand, the uncertainty margins are rather large. Okay, so this is actually something that is extremely sensitive to, say, for instance, the shear viscosity. The other thing that you can see is that somehow the initial state energy is consistently higher, actually by something like up to a factor of 2 or so in central lead conditions compared to the final state energy per unit rapidity. And this is simply due to the work that is performed against the longitudinal expansion. But so the real upshot of this is that if you consider how large of an error you get from variations of the shear viscosity here, this also shows somehow the potential of really taking the pre-equilibrium stage into account. Because if you could achieve some calculation with a 30 or 50% uncertainty of the initial state energy, then this would give sort of rise to a band like this. And so this guy is also this. So mapping the full evolution dynamics can then really be explored to somehow obtain combined constraints on A, what are the properties of the very initial state, but also what is the shear viscosity in the high temperature phase. Okay, so with that, let me conclude. So what I hope to convey to you today is that really over the past few years, we've made significant progress in understanding the non-equilibrium QCD, various patterns of non-equilibrium QCD with respect to the onset of hydrodynamic behavior and general patterns of equilibrations. I focused on implications for heavy-ion collisions. It would be interesting to work out also what kind of things can be learned with regards to the evolution of the early universe. So that's perhaps something that's for upcoming studies. I think the most important points for heavy-ion person is that really these studies have now reached a level of maturity where they can connect properties of the initial state that was there at the very beginning to the experimental measurements. And so they're ready to use for phenomenology. In fact, there's a sort of publicly available pre-equilibrium code called Compost, which kind of provides entirely macroscopic description of really the non-equilibrium QCD and heavy-ion collisions. And so I think establishing this link between what was there in the very beginning and what comes out in the measurement is really very important, because it somehow connects the physics that we see in heavy-ion collisions to various other physics experiments. After all, the initial state of a heavy-ion collisions is determined by the partonic distributions of the incoming nuclei and the way they scatter. And so, for instance, these small X gluon distributions, they determine both the initial state in nucleus-nucleus collisions, but also other processes such as, for instance, in PP collisions or an electron-ion collider. And so while we've made a lot of progress in somehow understanding the bulk pattern of equilibration in nucleus-nucleus collisions, there's also still a lot of interesting work to be done. And I think, so I've listed here a couple of avenues that I think are very promising to somehow further explore this interesting non-equilibrium phenomena in heavy-ion collisions. Okay, so with that, thank you very much. And sorry for going a little bit over time.
No, it's not a problem. Thank you for a nice presentation. I think it was very interesting. So let's go to our questions. We have the first question from Farid Taginavaz. So please go ahead.
Okay. Thank you for your presentation. I have a question about the relation between hydrodynamization time and thermalization time. Are they equal, or since I missed the link?
Yeah, so sorry. So this is what I was trying to convey over here on this slide. So I mean, so you have to, okay, so when you define a thermalization time, you have to say how you define it, okay? Because you can never truly reach thermal equilibrium. It's a time translation invariant state. But okay, I mean, one of the things you would expect for thermalization is, for instance, that the system becomes fully isotropic. So for instance, longitudinal and transverse pressures in the system become equal, okay? Now that turns out is a process that takes a really, really long time, okay? So even within hydrodynamics or so, this actually takes a very, very long time, okay? Now, hydrodynamics, okay, already becomes applicable before that happens, okay? And the reason for that is very simple. I mean, viscous hydrodynamics, or the theories of hydrodynamics in particular that we use in heavy-ion collisions, they're actually designed, okay, to describe the approach of a system towards equilibrium, okay? And so for that reason, viscous hydrodynamics becomes applicable on somehow much, well, you would expect it to become applicable on shorter time scales. In practice, it becomes applicable on significantly shorter time scales.
Okay.
So the brief answer is they're not the same, okay?
I have another question. Is it possible to ask?
Yeah, go ahead. But mute your microphone when you're not speaking, because
following
there are feedback.
this question,
Go ahead.
okay. I want to know, is there any microscopic interpretation of this hydrodynamization time, for example, in terms of 2-2 or 2-1 collision? Can you say anything about that?
Yeah, I think I can say a little about that. I mean, what I can show you is, so here you have, so this time I think here is what's called tau hydro in this earlier plot. So this is, I mean, so this is within a weak coupling description, what we find that the system looks like at around the time, you know, where hydrodynamization, or where you would start to describe it by hydrodynamics. I mean, in fact, you can still also see here some kind of remnants of the hard particles here extending over here. Yeah, but I mean, macroscopically, the system is well described by hydrodynamics. Yeah.
Okay, so next question is from Carl Ronsteiner.
Yep.
Yeah, hello. So very nice talk. Thanks. Yeah, I mean, my question is very much related to the previous one. And it's the question, if this, what you pointed out, that this hydrodynamic theory seemingly works almost outside its range of validity, how universal is this? Or is this a property of the particular initial state, which is sufficiently?
This is an excellent question, and unfortunately I didn't have time to address that, but I actually have this in part of my main presentation. Okay, so if you look at this plot over here, which is similar to the one I showed before, so here I showed the ratio of longitudinal pressure to energy density, again as a function of time in units of this equilibrium relaxation time, and then the black curve is hydrodynamics. The red curve is Yang-Mills kinetic theory. This is Boltzmann equation and relaxation time approximation, and the green curve are holographic calculations. Yeah? So in weakly coupled theories, what you find is that, okay, so first of all, what you see immediately, okay, is that around the time scale of order 1, okay, all of these have essentially relaxed towards viscous hydrodynamics. Yeah? Yeah. So if that is your question, then this, at least within the range of theories that's been studied here, this seems to be quite universal. Okay. Now for weakly coupled theories, there's an amazing thing that happens actually, is that the evolution follows kind of a universal pattern even earlier on. Okay, where you can see somehow here these gray curves. These are actually different. These are different initial conditions, and you can push this to even earlier times if you wish. They follow kind of a universal approach towards equilibrium. Now, this is no longer described by strict theory of hydrodynamics, so by the hydrodynamic gradient expansion, but there seems to be some kind of attractor curve, okay? And so this is what people refer to as hydrodynamic attractors. Now, at late times, this matches with the hydrodynamic gradient expansion, but there can be somehow memory loss or universal macroscopic feature even beyond the hydrodynamic regime.
Okay, thank you.
I see, that is okay. So the next question is Giorgio Torrieri.
Sort of as a question and a comment on two related things. This was following up the question I asked. In the middle, there was a lot of literature a few years ago that if you put in like a Vlasov term, the first thing that thermalizes is color. And color, there was the claim that color helps thermalize everything. So I'm wondering if your results will be qualitatively different if you include color, you know, unaveraged, because you do have color domains in the beginning, right? I mean, even if you don't have the color glass. As a comment, I would be very careful comparing with Kolmogorov. I mean, Kolmogorov is dominated by vortices. In 3D, you have vortices in every direction, so you have a cascade. In 2D, vortices can only point up and down, so you have an inverse cascade. I'm wondering if this is basically dimensional analysis. I mean, dimensional analysis in a high degree of symmetry. You see what I mean? Because the physics is...
Yeah, so this is, okay. So in part, I disagree with what you're saying, but in another part, I fully agree. So I mean, what I was referring here to is the theory of wave turbulence, right? So wave kinetic descriptions, I mean, this has been studied, right? Which is not necessarily only fluid turbulence, okay? Now you're asking a good question as to what extent, say, for instance, the scaling exponents that you observe, they can just be determined from dimensional grounds, okay? And this is indeed, so in this case where you have a self-similar scaling, okay, they can indeed just be determined from dimensional grounds. And in fact, they are the same for essentially all conformal theories in 3D, okay? Yeah, so you'll always find 4/7 and 1/7, okay? Now, in this case, you don't have self-similarity. What you have is actually, what you realize is a turbulent power spectrum, namely essentially this one, okay? And so in this case, the turbulent power spectrum, or the exponent of the spectrum essentially depends on the energy dependence of the splitting rate, okay? And this is, I mean, so again, you could think of different systems which have the same dependence. So in that sense, it's dimensional analysis, okay? But in this case, it is, I mean, it's the characteristic energy dependence of the LPM effect in QCD that gives you this, I think, 7.5 spectrum here. Yeah.
Okay. That was okay, right? So the next question is coming from Christoph Kutak. I'll read the question. Concerning low X transverse momentum proton densities, is saturation of gluons accounted for in your framework?
Yeah, I mean, so saturation of gluons would enter in the calculation of the initial state energy density. That's nothing I presented over here. Actually, this calculation that I showed here, where I said, okay, this is an initial calculation using really dynamical model for energy deposition, that is actually a saturation calculation. So that's an IP plasma model essentially. Yeah. But yeah, I mean, Christoph, if you believe that you can calculate, I mean, that you know gluon TMDs well enough, and you have a framework by which you can you can calculate the initial energy density in a heavy ion collision to 50% accuracy, I think that would be already very interesting. Okay, I think you could really learn something from that. Of course, yeah, I mean, one should account for saturation effects in this regard. Although, I mean, we have studied this in some cases and they didn't seem to be actually that huge. I mean, I would probably be more worried about higher order perturbative corrections.
Yes, I guess it's fair enough. So next question, Saeed Farid Gavi. Go ahead.
So my question is about you said that about this losing information from the initial dynamics in heavy ion. So I would like to ask about the proton-proton collision. Is it the same in a small collision system?
So this is of course the golden question, right? So the problem is essentially the following. Yeah, maybe I can explain this over here. So the reason that we're able to do these calculations in a heavy ion collision, or well, apply them to a collision of large nuclei, is that typically what we do in these calculations, because it's very complex, is that we essentially treat the system locally cell by cell, and we neglect the transverse expansion. Or we account for it later in a linearized fashion. And that is justified because the transverse expansion sets in later in a nucleus-nucleus collision, basically on a time scale somewhere, you know, a few Fermi or so, and the thermalization is fast on that time scale. Now, the problem is if you're dealing with a smaller system, right? So definitely a PA or PP collision is a much smaller system, then the transverse expansion and the system trying to equilibrate will somehow happen at the same time, okay? And so, so that's somehow a more complex calculation that you'd have to deal with. Moreover, it could happen that the system actually never gets to equilibrium and somehow becomes dilute, approaches the phase boundary, you know, before it has time to thermalize, and then really things would get very, very complicated. So that's a much more complex question, essentially because that separation of scales between transverse expansion and equilibration no longer exists in small systems.
Okay. I don't see any questions from the audience, but I did have a simple question, which is sort of slightly overlapping with the question, the last question. When you were discussing that the pre-equilibrium dynamics is hard to access because then many things are washed out by the essentially nearly equilibrium dynamics, I was actually sort of thinking there is an easy way out. If you consider something like proton-nucleus collisions where essentially you are not creating perhaps even closely anything equilibrated, then you will directly probing the pre-equilibration all the time, isn't it, right? Cannot you?
So indeed, I mean, so from a, I mean, I fully agree with your perspective, and I think there's a lot of potential to be learned from these collisions, right? I mean, in principle, this is what you want to do if you want to probe it, right? You want to catch the system while it thermalizes somehow and measure it, right? Exactly. So that's presumably the closest you can get to. The problem is just that in that case, it's very hard to calculate, right? So say you were to stick with a weak coupling, essentially what you'd have to do is you'd have to extend this to somehow include all the expansion types, and this is something that can be done. But then if you were to really try to account for the fact that now the system undergoes hydrodynamization in some non-equilibrium environment, okay, then very, very quickly you start to lose control over anything you do, okay? So there's a lot of things, you know, that are kind of make our life easier in the calculations in heavy ion collisions than in small systems. So while I deem this a very promising avenue in principle, it's also presumably the hardest one.
I see. Okay, I don't see any other questions. If I missed anybody, please reveal yourself and ask the question. I think I was keeping track of all the questions coming up. If we don't have any other questions, I would like to use this opportunity to thank our speaker, Sören Schlichting, for this very nice presentation. Thanks.
Yeah, thanks everybody.